Hi everyone, this is Dr. Stuckey. I apologize that I'm not going to be able to be at the live lesson with you guys tonight at 6 o'clock. I got sick at the end of last week and I just don't think my voice is going to hold out that long. So earlier in the day while I have a little bit, I'm going to go ahead and troubleshoot your questions for you. Alright, so the first one I'm going to work on is problem 648. So this is the problem where you have to choose which site to build your water processing plant. One of the tricks to this problem is to remember that when you're processing water, you've got two pollutants to remove, but every gallon of water you process removes this much of both of the pollutants. So that's one thing that some students in the past have struggled with a little bit, not truly understanding how water processing worked. So you don't have to do 1 gallon to get 0.3 of pollutant 1 and another one to get 0.25 of pollutant 2. 1 gallon of water gets 0.3 of pollutant 1 and 0.25 of pollutant 2. Right. Sorry. This student has done a really nice job with the structure of this problem and is having some trouble with linearity. So when you are troubleshooting linearity, one of the best things to do is go ahead and run a linearity report. So if you go to Solver and hit solve, you can see that it tells you the linearity conditions are not satisfied, and then you can click on this report that says linearity. And then when you go to this side, see what it says, linear function, yes or no. So these are occurring linearly. There's a problem with these. So these B, C, D, 12, when you look at those are the decision variables. So that means that there's some issue with how those are being used in formulas that is affecting linearity. So let's see if we can keep going and figure out what all we need to change. All right. So cells B, C, and D19 are all having issues with linearity. So let's go look at them and see what we can see about them. So B, C, and D19. So that's the amount removed. Yeah, and actually what we're going for with this is not the amount removed. We are going for water treated. This is our effective capacity constraint so that we don't choose to treat water at a plant that has not actually been built. And so we actually don't need the multiplication here. We just, because this is redundant, right? The effective capacity should be taken care of with whether or not the site is built. So what we want is this water treatment to be just whatever it is. So it's just a copy. You just need to reference that formula. There's nothing to do with it other than a reference. Okay, so we can copy that on across. All right, and so notice that this didn't change, but it, as far as what number you were getting, but it did change for linearity. All right, let's go look at the next set and see what else we can figure out. All right. Seeing the amount of pollutant 1 and 2 in B6, 15 and 16. So again, that's going to be how it's used. So let's go look in some of the, let's go look and figure out, oh, and it was B, 15 and 16. Okay, not D, right? Yes, B, 15 and 16. All right, so let's look at this formula. So suspect that there may be something in this formula that we don't need that's affecting linearity. So what are we doing here? All right. And again, we don't need to constrain it. We don't need the site built constraint. So if we take that out, believe it work. And let me explain why we don't need the site built constraint. So all we need to know is the amount of water actually treated times the amount of that pollutant that was removed. And the reason that's the only thing we need to know is we've already constrained this effectively to be 0 if the plant isn't built. So when you're putting it in again, like I said, it's causing issues with linearity. All right, now let's rerun this and see if we get the correct answer. And we do. So that fixed the issues of linearity. Everything else was spot on with this model. And the student did a great job. Those formulas actually worked mathematically. Other than that, they violated linearity. So the model was really solid. Like I said, just a couple of issues with linearity. Anytime you run into that linearity issues, again, run the linearity report so you can see what specific cells you're having issues with. For anybody else who's looking at this, I want to go over how to do this effective capacity. He nailed it. The student that did this absolutely nailed this formula. He did a fantastic job. And let me explain to the rest of you what he did and why. So, first of all, ignore this B10. We'll go over that in a minute. He did a max formula, okay, to figure out what are the maximum number of gallons that would have to be treated at this plant in order to remove the required amount of the pollutants. So I actually want to break that out a little bit more so you can see what we did. So I'm going to do it in a couple different cells. So pollutant 1, site 1, okay, you're required to pull out 80,000 tons of pollutant 2. You get 0.3 per gallon that's run. So you do 80,000 divided by this 0.3, okay? That means you have to run 266.666667 or whatever gallons, or 266,666.66 gallons of water in order to remove the required amount of pollutant 1. Let's calculate pollutant 2. And this is at site 1 and only at site 1. So pollutant 2 divided by the amount removed. Okay. All right. So what a max formula would do is say if you built this plant, we have to pull out the required number of both. That means that we're going to be the bigger number here is pollutant 1. Okay, so that means that we're going to have to treat 266,000 and change gallons of water in order to pull out the required number of pollutant 1. We only would have had to pull out 240 gallons to treat pollutant 2. What that means is that we're going to actually pull out more of pollutant 2 than is required because we have to treat all these 266,000 gallons of water. Now, the reason that you also include whether or not the site was built, which is this B10, is so that if you choose not to build the site, that it zeroes out and you don't allow any water to be treated at the plant. Because if you can treat water without building the site, that would obviously be the most cost effective. However, for obvious reasons, that's completely impractical. So we have to know we can only treat water at the plant where that was actually built. Okay, so that's the point of that constraint. I hope that helps explain it to you a little bit. And again, I'm so sorry I'm not going to be able to do your live lesson tonight, but I hope this helps a little bit. If you need some further clarification or if you want me to look at your own model, you are welcome to email me. All right. Hope you all have a great afternoon and evening, and I am looking forward to seeing you at the live lesson next week. I am going to do, I'm going to go through my email, and I'm going to do anybody who sent a model to me so far, I'm going to go ahead and troubleshoot for you. So I think I'm going to do 50 as well, if I remember correctly. All right, stay tuned.